Good afternoon and welcome back to this series of webinars dedicated to masonry buildings. Today I'm going to talk about a rather particular topic which consists of existing masonry buildings that because located in areas not subjected to natural seismicity, so seismicity due to having a tectonic origin, can be particularly vulnerable to seismic action even when this action is not originated by an active fault system, but is rather generated by human activities. We will see how a particular case gave rise to a series of experimental and numerical studies that have general validity and allowed us to investigate in depth some aspects that are relevant also for buildings subjected to seismicity having a natural origin. In this slide, we can see a scheme of human activities that can cause seismic events. Now, when we talk about causes, we have two different situations. We can talk about seismic events that are literally induced by human activities, for example, related to the extraction of hydrocarbons from the subsoil, and which can cause earthquakes where normally no fault system capable of generating earthquakes are present. On the other side, we can have cases in which human activities create the condition for a natural earthquake to develop in an already existing fault system. Here you can see some example of possible causes. First, we have the extraction of hydrocarbons, which are stored in the subsoil. Now, in this case, the extraction alters somehow the equilibrium condition present in the soil layers, and that can cause internal collapses, wave propagation, and therefore earthquakes. Shale gas exploitation is another example, and the mechanism of formation of earthquakes is quite similar to the one of extraction of hydrocarbons. Another possible cause is the exploitation of geothermal energy. Now, of course, this is not the case of a single house, but it can be the case when this activity is carried out at a larger scale. An example of this case is the city of Basel in Switzerland, in which a large project for the exploitation of geothermal energy was activated in the past, but had to be stopped due to small earthquakes that were generated by this activity in an area already subjected to seismic risk. Hence, the city of Basel was destroyed by an earthquake in 1356, so it is an area where natural earthquakes can occur. Another case of possible causes of earthquakes is the case of mining operations, in which the so-called rock burst can occur. These are collapses of mining tunnels that lead to the propagation of waves that are then possible generating damage into the buildings, which are normally to the buildings that are just above the tunnels. There were cases of this type, for example, in Poland or in South Africa. An emblematic case is the seismic activity in the central and eastern United States, in particular in the states of Oklahoma and Kansas, where seismic activities anomalous with respect to the historical trend occurred starting from 2009 and gradually becoming more intense, also causing earthquakes with a magnitude of around 5.8, so not negligible, in areas where no seismic or at least very limited seismic activity was present, both in the number and also in the intensity of the earthquakes. The case we are focusing on today is the case of the area around the city of Groningen in the Netherlands. As you may know, in the north of the Groningen province, there's the largest underground gas field that we have in Western Europe. It is a large field and it's also, of course, an important economic resource for the Netherlands, which have based part of their economy on the extraction and sales of gas. But it's also a resource for Europe. For example, you have to remember that the pipeline, that is the gas pipeline that is coming to northern Italy, is arriving directly from this field. Now, since the beginning of the 1990s, earthquakes began to be observed in this area, which is an area without a historical record of earthquakes of natural origin. Later, these events were recognized to be induced events, induced earthquake due to the gas extraction, since they were due to internal collapses of the subsoil as a result of a loss of equilibrium, of internal equilibrium due to the extraction of gas. Now, the most significant events took place in 2012 and 2018, with magnitude around 3.6, 3.4, which, by the way, was enough not to, of course, luckily not to cause victims, but to create damages to the buildings. So this led to the activation of a series of studies, both on the mechanism generating earthquakes, which is related to the quantity of gas extracted, and especially on the consequences or on the seismic risk due to these earthquakes in an area that, I want to underline, having no seismic history, is obviously characterized by buildings not designed to withstand earthquakes. Now, this area is poorly developed from an economic point of view, except from this underground wealth that was exploited to gain a certain level of prosperity. Buildings in the areas are mostly made of masonry buildings. Hence, masonry buildings are representing around the 90% of the building stock, the residential building stock in the area. And this holds for both for oldest buildings, typically made of brick masonry, but also for modern constructions, in which maybe other technologies are used, but we will talk about later about them. But again, they still are masonry buildings. Buildings in the area are obviously designed for vertical loads. Sometimes they can have problems related to settlement of the foundation because they are located on a few meters above the sea level on layers of sand. Whereas regarding the horizontal actions, they are calculated only for wind actions. The characteristic of this construction is obviously that they are not designed to withstand earthquakes, and therefore the first question that we would like to answer, we wanted to answer, is what is their seismic behavior? You can see also that this structure have architectural features that are peculiar with respect to, for example, the buildings that we have in Italy, because they are characterized by a large amount of openings, as you can see. Furthermore, there is no history of observed damage. There are only small damages due to the first events. So the question is, which damage mechanism can take place in these buildings, and also which can be the consequences, the victims in case of collapses of these buildings. I want to underline, before going on, that these earthquakes are related to gas extraction. Therefore, one can think, okay, if I'm stopping the gas extraction, everything will come back, will become okay. But actually, this is a process that in reality would go on for a few years, even in case of stopping the gas extractions. To face this situation, the company in charge of the extraction of gas in the area decided to activate a large research project to try to answer the question that I was posing before. It involved, among the others, also the EUCENTRE Foundation of Pavia. In this research, it was possible to study the behavior of the structure in the area by carrying out a wide experimental campaign. Now, the research started with the study of the structural features of the building in the area, and then continued with some in situ tests. If you remember, I was discussing these tests in the webinar dedicated to buildings knowledge, with the aim of getting information on the mechanical properties of masonry. Then, laboratory tests were carried out on structural components, both in plane or also out of plane, in plane and out of plane. And then a series of tests on the shake table, were carried out considering portions of buildings or entire buildings. Among these tests on buildings, you can see here, for example, a first test on a two-story terraced house building. I will discuss later about this structural typology, that was carried out in 2015, followed by two tests on detached houses carried out in 2018 and 2016. And another test of another building, which was carried out in 2018, again considering a terraced house building. The information obtained allowed to arrive to a useful knowledge of the seismic behavior of these structural typologies. And that was useful, on one hand, to create numerical models with the aim of then extending this modeling activity to a variety of case studies representative of other construction typologies in the area. And on the other hand, it was useful to define specific assessment strategies for the seismic verification of these type of structures, with also the development of guidelines of building codes. And finally, this knowledge was also useful to try to think about compatible and effective retrofit systems. This obviously required to reproduce during the construction phase of the prototypes in the lab all those characteristics of these characteristics and structural details that can be found in the buildings in the area. For example, so it was first necessary to do a research on the characteristics and construction details and the materials that are used in the area. Then it was necessary to reproduce the mechanical properties of the buildings. For example, a mortar with a composition designed to take into account a certain level of damage was adopted in the specimen built in the laboratory. Furthermore, to avoid doubt that the construction reproduced in the laboratory were in some way affected by the better or at least different workmanship of the Italian masons, we decided to call Dutch masons to build the specimen in the lab. Together with tests on structural elements and buildings, a series of ancillary and mechanical characterization tests were also carried out on the component of the masonry assemblage. For example, tests were carried out on mortars, on bricks, and on small masonry assemblies subjected to in-plane and out-of-plane loads. In particular, compressive tests were carried out to determine the compressive strength. Bond wrench tests were performed to investigate the tensile strength of the joints. Triplet tests were performed to investigate the in-plane shear strength of the joints. And finally, also tests were performed to investigate the torsional shear strength of the bed joints. Now this represented a series of comprehensive and in some cases also original tests. This complete mechanical characterization was also useful to develop numerical models that were based on the properties that you can find, the real properties, the real material properties coming from the test, and also models capable of taking into account the variation of these mechanical properties. Here you can see the test on a wall building belonging to the detached house typology that was carried out at the LNEC laboratory in Lisbon. Here, as you saw, the problem was not really the global in-plane response of the construction, but was more represented by the local response of some elements. For example, related to the very flexible roof and gable walls system, which is amplified, whose response is amplified due to the amplification of the ground motion along the height of the building. Another problem that we wanted to study with this test is the behavior of non-structural elements, such as the chimneys, which are among the most vulnerable elements of these constructions, and whose response is also worsened by the amplification of motion. Regarding the global response associated with the in-plane mechanism, you should note that the behavior of masonry walls tends to be a behavior of rocking with the formation of roughly horizontal cracks at the ends of the piers, rather than damage due to shear. And this is due to the shape of these walls that tend to be quite slender. After the tests, damage survey was performed, together with the identification of limit states. From this figure in the middle, you can see how damage is characterized by cracks at the top and bottom of the piers, and by shear damage in the spandrels. For example, here you can see a picture of this damage. Then you can also see a separation between the in-plane loaded wall and the out-of-plane loaded wall. And this is due to the activation, to the combination of the in-plane and out-of-plane response. Damage thresholds were finally identified in terms of angular deformation or drift, referred to the displacement of the roof base, or also associated with the local behavior of masonry walls. In addition to the tests on buildings, experimental tests were also carried out to study the behavior of single components, single walls, subjected to out-of-plane excitation. Firstly, the flexural out-of-plane behavior of walls released on the vertical edges was studied. In this case, the wall is subjected to unidirectional or uniaxial bending. Then, the more complete case of walls with vertical edges restrained by the presence of transversal walls was studied. And in this case, the wall is subjected to biaxial or bidirectional bending. These tests were useful especially to calibrate numerical models to foresee the behavior of entire buildings, combining the vulnerability to global in-plane mechanism with the vulnerability to local out-of-plane mechanism, and possibly also to study the behavior of some non-structural elements, such as chimneys or parapets, that are characterized by out-of-plane response. Here you can see some of the results of these tests. For example, in this first figure, you can see the result of uniaxial bending test. You can see how the envelope of the cyclic force displacement curve is well approximated by bilinear or trilinear behaviors, which are the models and the laws that were that are commonly used also in code-based safety checks. So the models of the nonlinear kinematic analysis that are characterized by a decrease of the shear of the force with the increase of displacement due to the p delta effect, to the second order effect of masonry. Now, in case of bidirectional bending, greater energy dissipation is evident from the test. This is due to the fact that in regular brick masonry, in order to open cracks activating the out-of-plane response, there must be displacement and rotation inside the mortar joints. There are therefore friction phenomena which are responsible for this dissipation, for this large dissipation of energy. Now, this is a single degree of freedom numerical models that was developed at the University of Pavia, able to capture the behavior of a structure characterized by out-of-plane behavior. The model is able to reproduce the observed experimental behavior after an appropriate calibration of some parameters, which, however, are quite limited in number. Hence, it is necessary to specify as input the geometric and the mass properties, which, by the way, are known parameters, and it is necessary to calibrate the coefficient related to the dissipation of energy. Now, this can be done essentially in two ways. Firstly, through the so-called coefficient of restitution, which is a parameter controlling the energy returned after a collision and the one dissipated during the same collision. Or as an alternative, the equivalent viscous damping can be used. Now, once the energy dissipation is somehow calibrated, even with such a simple model, it is possible to capture the experimental response. As you can see here from these plots, in which the red curve is the numerical response, which is very similar to the black curve, which is the experimental response of the walls tested. The most common and vulnerable building typology in the area is represented by terraced houses that I was also mentioning before. These are blocks of typically 4 units, mainly made with a wall typology characterized by cavity walls, which is made by 2 leaves of masonry with a cavity inside. Normally, the external leaf serves as cladding and protection for atmospheric agents, whereas the internal leaf has the role of carrying vertical loads. The internal cavity serves as insulation against thermal actions and actions of wind and rain acting on the external leaf. We studied the behavior of this typology by reproducing in lab an end unit of one of these rows and then testing it on the shake table. This test was done in various stages. On the left, you can see the very first test carried out on the entire end unit at the EUCENTRE Foundation of Pavia. On the right, you can see the second test, which was carried out on the shake table of LNEC in Lisbon, which was reproducing only the upper floor and the roof of the first specimen. Finally, first test was carried out in Lisbon, in which only the roof and the gable walls were reproduced. Given that residential masonry buildings are up to 90% of the total amount of residential buildings, and given that more than half of these masonry buildings in the area are made with terrace house typology, this typology is the one having clearly the greatest impact on the seismic risk in the area. Most of the buildings are made with cavity walls and are typically made of 2 floors. In some cases, also three floors are present. Obviously, this is a more vulnerable condition. Normally, they have a large amount of opening, especially in the longitudinal walls, which are the ones along the street. This also leads to rather short and slender masonry piers, which are able to offer a limited resistance to horizontal actions. There are different varieties of floors. The most widespread type is reinforced concrete slab, but in some cases also precast slabs are used, whereas roof is normally made of timber. Here you can see some details of the tested prototype. Materials are different in the internal and external leaf. Typically, the internal leaf loaded by floors is made of calcium silicate masonry, at least in the most common typology. Modern typologies still use calcium silicate, although in larger blocks rather than bricks, but essentially the material has remained over the years due to economic reasons. The external leaf, on the contrary, is made of clay brick masonry, and the two leaves are connected through the thickness with steel ties, like the one you see in the yellow circle, having a diameter of 4 millimeters. In the specimen, two ties were used over square meters, whereas in reality they tend to use only a single tie over square meter. Also, the connection between the floor and the walls was accurately reproduced. As you can see, the floor rests on the transversal walls and is simply connected to the longitudinal walls by means of connectors. The external brick wall, on the other end, is not loaded by floors, but can be slightly loaded by the roof. Here you can see the details of the gable walls and the roof. Gable wall is loaded by roof, which is usually made of timber, and a connection between the gable and the roof system is made also with these steel connectors. Here you can see the experimental tests, and you can appreciate that also with an earthquake even stronger than those reasonably expected in the area due to induced seismicity, there are actually no collapses in this building. However, there is a widespread damage. In-plane loaded piers are hence characterized by predominantly flexural behavior with horizontal cracks, whereas transversal walls are characterized by significant cracks related to the activation of out-of-plane mechanism. And in-plane loaded spandrels have shear damage, both in the internal and also external leaf. Here you can see more images of the damage in the calcium silicate leaf. In particular, you can see some X-shaped cracks in the spandrels, represent typical of a shear damage. And here you can see some horizontal cracks in the piers and stepped cracks in the transversal walls. Here you can see other images in the clay leaf of cracks in the clay leaf, particularly again X-shaped cracks in the spandrels, and also vertical cracks at the edges of the spandrel. A substructure of the same building was then reproduced in the laboratory in Lisbon, using same materials, same workmanship, and same structural details of the first houses, reproducing only the upper floor and the roof. The signals recorded at the first floor during the previous test were used. In case of this test, it was also possible to study the simultaneous effect of the horizontal action and also of the vertical component of the earthquake. Here you can see the test. The simultaneous action of the two components in this case had a very significant effect. However, the collapse that you saw was not really due to the vertical component, but to the fact that this pier was having an in-plane rocking behavior, and it was rotating around this right tube, uplifting the left side of this pier and also uplifting the slab resting on it. So this transversal wall became unloaded and therefore collapsed. Here you can see the damage observed in collapse condition. Particularly, you can see the horizontal cracks of this pier that was having flexural behavior characterized by rocking, and you can see the out-of-plane collapse of this transversal wall. From the comparison of experimental results obtained for the two investigated typologies, it was possible to understand how terrace houses are actually the most vulnerable typology. In particular, the comparison with the detached houses, which is the second most common typology, shows a substantially double shear capacity of the detached houses with respect to terrace houses. Here you can see the damage and limit state identification job done for the detached houses. Damage states are represented by these different colors, and here you can see that specimen tested at EUCENTRE is attaining heavy damage for a lower drift with respect to the other specimen that was the one tested in Lisbon. Limit states correspond to the attainment of each damage state. Drift thresholds for in-plane behavior were then associated with each limit state in terms of interstory drift. This information is also useful for defining the limits to be used in code-based safety checks. Now, this slide reports the results obtained for the detached house building specimen tested in EUCENTRE in Pavia. Here you can see the damage and limit state identification job done for the terraced house typologies. Drift thresholds are lower than those associated with detached houses and are consistent between the specimen tested in Pavia and the substructure tested in Lisbon. All this information allowed to carry out a numerical modeling activity, which turned out to be very, very important. The Tremuri software in its academic version was used. Firstly, a model of the terraced house specimen tested at EUCENTRE was developed, including some peculiar features to capture the behavior observed experimentally, but always respecting the equivalent frame modeling philosophy and using mechanics-based macro elements. Here you can find some details of the model. You can see that gable walls were explicitly modeled, out-of-plane stiffness of the diaphragms was modeled using additional reinforced concrete beams. Out-of-plane contribution of transversal wall was also modeled. These are all non-standard features, but always respecting the equivalent frame modeling philosophy. This modeling strategy proved to be extremely accurate in predicting the experimental response. Here, for example, you can see the progression of base shear as a function of the displacement achieved in each run of the test. There is a substantial correspondence between the experimental test and the numerical model, and this can be also found at the level of the single run of the test. So if you compare, for example, the force displacement curve obtained at the last run of the test, you can see a good agreement between the numerical prediction and the experimental response. And also in terms of damage mechanism, there's a good agreement between experimental and numerical simulation. The availability of a calibrated model allowed to extend the analysis to raw buildings. So the single end unit that was tested and modeled was then extended, modeling the entire row of buildings, reproducing the same unit several times. The geometry was then changed a little bit, creating a transversal widening using a more realistic width of the structure, and also considering the even more vulnerable case obtained adding a single story at the top. Nonlinear dynamic analysis were performed on these models with the aim of deriving fragility curves for the global in-plane behavior. Fragility curves are curves representing the probability of exceeding a certain damage state given a certain level of the seismic action, and are a common measure adopted to quantify the vulnerability of structures. In this case, nonlinear dynamic analysis were performed on the models to calculate the drift demand that was then compared to the limit state thresholds identified experimentally to obtain the probability of exceedance. In this case, the seismic action is expressed in terms of peak ground acceleration. As you can see from the left figure, a raw building, which is represented by dashed lines, is slightly less vulnerable than the single unit. And this is somehow expected since a minimum collaboration between the various units inside the terrace house is normally present. However, a similar behavior remains in terms of global fragility, at least for the most significant limit state, which are the severe damage and the collapse limit state. Among the results of all these dynamic analysis, we can say that the most important results are two. And first are the confirmation of the adequacy of the equivalent frame modeling approach for the analysis of the global behavior also of these quite peculiar building typologies. The other result is the confirmation of the effectiveness of the approach adopted for modeling the out-of-plane behavior, or generally speaking, of the local behavior, through single degree of freedom models having bilinear or trilinear behavior, which are also the models used in professional practice to perform cost-based out-of-plane safety check. The results obtained were also the basis for the development of seismic vulnerability assessment strategies that were then applied to a series of buildings representative of the different construction typologies of the area and that couldn't be experimentally tested. Here you can see 8 buildings representative of 8 considered building typologies. Here you can see the Tremuri model that we developed for the representative buildings. You can find, for example, the terrace house building, the detached house building, and also more urban and city buildings like this one or that one that you can find, for example, in larger cities such as Groningen. Finally, it was possible to develop a comprehensive strategy for the assessment of seismic safety that included the global behavior and the behavior of secondary elements, for example, roof gable wall system, or also non-structural masonry elements such as parapets and chimneys. All these results were used also to develop building codes or generally guidelines for the seismic assessment of the buildings in the area, or to design retrofit intervention of the buildings. Now, regarding the development of building codes, I would like to stress that these results, together with other results, were used to develop a new building code that was issued in 2018 and also with a review in 2020, and that is the one used by engineers performing the seismic assessment in the area. And we were also involved in the development of a module of the software Tremori, which was consistent with this new code, and that could be used by engineers in the area to perform the seismic assessment. Now, before finishing, I would like to say a few words regarding retrofit intervention. Because in the same experimental campaign, a prototype belonging to the most vulnerable typology, so a prototype of terrace houses, was used to evaluate experimentally the effectiveness of a recently developed retrofit strategy, characterized by reduced impact on the construction and also reduced cost. Now, the retrofit consisted of timber frames connected to the inner leaf of cavity wall, masonry wall. The improvement of the response firstly consisted in preventing the out-of-plane response of the wall. However, by adding some tie-down connection, it is possible to increase also the in-plane flexural strength of the wall. And finally, by nailing timber OSB panels to the frame, therefore to the wall, it is possible also to increase the in-plane shear strength. Now, to test the efficiency of this system, the same building was tested in two configurations, a bare configuration, so a retrofit configuration, and another configuration applying this retrofit system. The test demonstrated that there is an increase of performance of the retrofit building, which is evident from the comparison, for example, of these two curves, because as you can see, the gray curve, which is the envelope of the experimental test on the retrofitted building, show larger capacity and better performance with respect to the black curve, which is the bare building. Now, this solution is also easily applicable to existing buildings. With this, I've concluded my presentation. I hope this presentation was interesting and that you could have got some aspect useful also in the seismic assessment of buildings subjected to natural seismicity. I want to thank you for your attention, and I hope to see you again in the next webinar. Goodbye.